So I'll get started. I'm going to brush through a little bit of it because it was like some of it was like more for marking criteria purposes, not really informative purposes, because I'm reusing some of these slides. So I'll begin with my one. So that's the full name of it. So robust FPGA-centric CNN. Basically what it means is that I need a good machine learning algorithm to run on an FPGA, and I want to use it on GPS-denied drones. So like drones that don't have GPS, they want to use the camera to see where they are. So my supervisor's Matthew Souza. So I guess like the situation that you might find yourself in if you're a drone is you can see what you're above, but you might be like, where am I in terms of everything else around me? And this is a problem that like some people obviously have. There are companies that actually work on this. What's different, I guess, about my project is that most companies would opt to use something like a Jetson or like a GPU-based solution, just because it's easy and pretty industry standard, and except the growth of GPUs is like much faster than FPGAs in terms of compute, like in the recent years, at least for like something that would fit on a drone. And so there's like pros and cons of both, but I won't go too much into that. But the main gist is that mine's a little bit different to what currently exists because I'm doing it on an FPGA. The concept of this localization isn't like necessarily new. And so yeah, that's the goal. It's like you want to have that picture and the drone needs to know like, where am I given a reference image, right? And that could be, I estimate the pixel coordinates, but it could be easily translated into like GPS coordinates or whatever you wanted to do. And so I started off, that's basically what I just said, that there's a few traditional approaches. CNNs are a good one to do. And I changed my approach a few times. I was initially going to use the university hardware, and I was like, that's a bad idea, because it wasn't really going to work very well with, well, it just would be very hard. So a traditional approach might be where you're not using a neural network, you're just using a kind of like a feature recognizer, which is, I guess there's likenesses, but not really. It's just going to learn points, it's going to learn groups of pixels, and it's going to like basically hard code that. It has no sense of generalization. And basically that's not super ideal. I tested that out and just wasn't very robust to do. It's fast, but not really robust. Basically, if like a bomb hit a building, it's not going to recognize the building. That's kind of like what would be bad about that approach. And then so I swapped from like what the university would have, they have something like this, to something like, I bought one of these because these are the same price but have roughly double the performance, because these are an ultra-scale plus FPGA. Basically just a better, it's just better, but in Australia they're the same price for some reason. So I don't know why that is. And so just for comparison, so some platforms I might compare to, so there's different kind of solutions to do graphics processing like a CNN. So CNN's convolutional neural network. That's basically just like image recognition. Typically, you can think of it like that. And so there's a few approaches you might want to do for like a small device that can go on a drone if you want to do like image recognition. So like the main ones are going to be maybe something like a TPU that goes into a Raspberry Pi, or a TPU that goes into some sort of other embedded device. The industry standard basically is like a Jetson, because NVIDIA's chips, they're such a big company that they can like grow their chips and like the performance really fast compared to other companies. So basically the performance of these are, and you can see, so like the KV2CC, which is what I'm using, is actually like quite older, like a few years older. And then the Jetsons will have new ones coming out as well, obviously. But if a new FPGA-based system were to come out now, it might be more competitive with the Jetsons. But as it is now, basically all of the smaller FPGAs are kind of like left behind in performance somewhat relatively compared to the Jetsons. The Jetsons are just getting updated like way more frequently. So that's just like something to note as to why someone might use an FPGA or not. I've specifically gone with an FPGA because of like the thesis requirement that I use an FPGA, and it makes my research like different. So I just wanted to clarify that, because some people obviously be like, why don't you just do this on a Jetson? And the answer is, in industry, you probably might want to do it on a Jetson, probably. But there are reasons why FPGAs are sometimes good, and I'll come to that. That's just some comparisons, but basically, oh, sorry, that's not comparisons. I should note that when you use an FPGA, like the FPGA that I've used, all of these devices have like a completely different way that they operate. Like they've got their own like operating systems, their own like, the actual processor is obviously physically different. It's just like very different systems for each of these like devices, right? It's like Apple or Android. It's like they're just very different. And so this is just mentioning what that is about. And so when you run Pedal Linux, that's what you run, or at least what I run. You can run anything. The FPGA is very customizable, but what I run is a Pedal Linux distribution that they provide to make things easy. And like it provides some like monitoring. So if I wanted to log like power usage, it has those features already implemented. Which if I were to even just try and do something as simple as this myself from ground up on an FPGA, that would take extremely long time. So like I've kind of just tried to use as much as possible provided by the AMD people. And so this is generally what it would look like, right? Like on some FPGAs, it's just the FPGA processor, and you can think of an FPGA like this. So a typical CPU or a typical processor is like a pre-configured device. An FPGA is like, you can configure it however you want. That's like that's the in and out of a CPU versus FPGA. The FPGA on the right, you could turn into kind of whatever design you wanted, like in theory. And so for the FPGA, this is typically how you would put it on there. It's not super useful to know. This is like the main thing, is that you have a DPU that you assign. So my board that it comes with has a processor component. The processor component handles all the generic stuff. But then the actual machine learning side, I'm offloading to the actual kind of FPGA, and I assign to the FPGA a DPU design, which just means digital processing unit. Basically, someone smarter than me has come up with an optimal design for some sort of machine learning application, and they've designed this general purpose DPU. So they've essentially, they've done this job for me. They've created something like this that will work on the FPGA, and they've done that for me. All I have to do is load it in. I have to pick which one I want and load it in. And it's not super meaningful. It's like a big topic, but that's just generally kind of what would happen there. And so the first thing I did was run the tests that like the demo. I tried to just run that demo because that took still like a week. So not a week, like, a week of doing a bit here and there. So the first thing it was to do was to predict on an image using any machine learning model, not my model, just any model. And so I predicted that this was a brain coral. So I got that working, and I was like, yep, like this is so easy. Well, that was the first time I got anything actually running on the DPU, like running on the FPGA, like a machine learning model. So that was I was pretty happy I got that working, because there's there's a lot of moving parts. And so what you typically would do is you develop your model, you train your model, and then you want to quantize it and prune it. So when you develop your model in Python, it's probably going to be like 12-bit floating point or whatever it is, right? Your model's going to have really accurate integers. But then put it on the FPGA, it uses 8-bit. So it's going to squish all those numbers down, and you've got to do a specific workflow to do that. Then once you've done that, you need to compile the model to that DPU. So I've specified I need a particular size DPU, and then I need to tell it, okay, you need to fit this model onto that custom DPU that I've elected. So there's a few steps to it, but basically I did it on a preliminary test and it worked pretty okay. But the problem was that getting my actual model was quite difficult to do. And in order to do that, you essentially declare, like on the right hand side, I declare like my model. And then, so like here, you have essentially, I'm just like showing you this reference. You have to use this Vitis AI library they've got separate to your project to compile it. Like you have to compile it using their Docker container stuff. If you ever want to do this, you've got to keep that completely separate to your project. So this compilation step of actually getting the model onto the device for the first time you do that is like quite challenging. And so one of the challenges you might encounter is my initial model at the very end of the model. So imagine a big long pipeline of things that the model does. And this is like broken down at the very end. You've got like a particular layers of your model, right? Like bits of it. This one here, on my first attempt, didn't work. That's why it's red. And the reason for that is that this isn't supported. I compiled the model, right? It compiles successfully, and it's like, yeah, I compiled all good. But it's actually not all good. You have to inspect it and check that none of these are red, basically. Because what it means is that it can compile it, but it like just omits the layer if it doesn't know what it is, which is like this red one. And so you have to implement this separate, but what you actually should do is you retrain your whole model and change these ones out. So here I've used like a sigmoid activation, but sigmoid activation isn't supported by AMD in this pipeline, so I had to change it to a hard sigmoid. Does the same thing, different function, like slightly different function. And then it's blue. Basically blue means good, runs on the GPU. And so there's like lots of these little steps on this compilation pipeline. I just kind of wanted to show a little bit of it. But this is more interesting. So how do I actually test like the model? So I developed this way of testing. So I have on the right hand side, that's the actual like FPGA. I have it plugged in via Ethernet to my computer, and then I talk to it. So Ethernet for file transfer, and I use like a little USB. So that's like this. I use that one to just talk to it like over the shell. But then I've got the Ethernet plugged in, doing file transfer. And what I'm doing here is this is a software emulator on my computer where I'm emulating that it's on a drone. So the FPGA board thinks it's on a drone because it's getting shown that square, and it thinks that it's the X. And basically what happens is that the simulator sends that to the FPGA. The FPGA, so that ML gets run on the GPU, so that's the blue one, it's really quick. And then it sends it back, because it's like talking over this Ethernet connection, which is orange. Comes back, estimates where I am. The drone says, I think I'm here. This is like go right, go left. It goes right or it goes left. And it's got to go between all the points. And you can see that when you actually run it on the hardware, there are inaccuracies. And that's why it doesn't quite go to the points. Like it's a bit off, right? And so that's kind of like one way I can measure, I guess, like general inaccuracy. Because I need to run lots of different simulations at the end of the day to test whether it will work real work, because you don't really want to put it up in the sky if it's not going to work. And so this is like just like a quick video. I'm not going to show all of it. It's just like, you get the general idea, right? Like it's a simulation. The drone, wants to go wherever it's going. I'm pointing at some stuff, but you get the idea, right? Like the drone's trying to go somewhere, and the software is tricking the drone into thinking it's really flying. And so that's how I like test that stuff. And so then, how do I actually make the model better? Because right now it's basically only using that singular image and lots of small versions of it to learn from, which isn't realistic to the actual environment. So what I used is this new Google Flash model. And so this is my typical image I've been using for training. So I generated a couple hundred of images on the right-hand side, which I'm able to do. I have like a few prompt templates, mixes all of them together so that I've got a potential 10,000, 100,000 different prompts. It just randomly elects the prompts. And then it's going to perform these alterations, and it's just like crazy how good it is. Like it can go from that to that one, or that to the top right one. It's just like super good for training models, honestly, because getting data like this would just be impossible otherwise. And here are another couple samples. Like from that same image, it was able to generate pretty realistic reflections and even completely different angles. Obviously, I don't train on any of those ones, but I think it's still pretty impressive that that's kind of how far the models are coming along, and that we can just access this. That was like I think it's like 3 cents an image or something. And then basically what I did is I've incorporated all these new augmented images, all these different types of images. It trains pretty good. The error with all these different images actually got worse, right? But that's expected, because even though it gets worse in simulation, it's getting better in real world scenario. And so here it gets about 150 pixels error. Basically, that's like 8 to 10% error. And the other thing as well, at different altitudes, I kind of measure like different altitudes, like how far you would in theory be up in the sky. And you see that generally as we zoom in, so as we go closer to the ground, the performance gets worse, which intuitively makes sense because you're able to see less time marks. So yeah, and there's obviously more testing I've done than this. That's just kind of all I can show for now. Next steps basically would be to continue these augmentations and just in software simulate the model best I can to get it improved, and then maybe put it on a drone. But I'd only put it on a drone once I'm like convinced it actually works. And one of the ways I actually test that is I have like on like my biggest monitor, I put the image up. So I put like a random image up like this, and then I use a webcam and actually like hold the webcam up over it like this, because that's going to be like really challenging. And so it's not very good, but it would be like, if you divide it into maybe like 8 parts, it's accurate to like that. So it's not very accurate, but it's still encouraging that I can even get in the right 8 using a webcam on a screen. Like it's got a pretty horrendous chance of getting that right. But so the next step is just finalizing it, putting it in the report, seeing how far I can get. And Matt D'Souza said, don't worry about testing against a Jetson because he thought Jetsons were too annoying. So I was like, okay, plus work for me. Yeah, that's all. So thanks for listening. I went much longer than I thought. I went for 20 minutes. I was meant to be 10, but yeah, thanks. Any questions? If there's no questions, there is a question? Yeah.
So you said you have to like compile your Python code for the DPU, right? Mm-hmm. I noticed you use PyTorch for that.
Yeah.
Like, does that process of compiling from Python to DPU only work for certain Python packages? Like if I were to use like some random Python package, would that still work with the compilation process?
You basically just use PyTorch. Some TensorFlow is supported, so if I go back to, might be one of these. I think here, it might say TensorFlow. There's a particular graph, I don't know if it's here. I don't think it is. But basically, there's another graph on that documentation that looks sort of like the grey one, and it's a bit taller. Basically, if you were using TensorFlow, they've got some of their own compilation tools for TensorFlow. If you're using PyTorch, they've got some tools for PyTorch. If you're using any kind of other other libraries, I just wouldn't. Like this is basically going to be for people that are making completely custom models. Like if you can load in other people's models and everything, sure, but you've got to have it in like PyTorch or something like that. Like you've got to basically have this representation of it, which looks like you've got to have some sort of representation like this. If you don't have this, as long as you have this and the actual compiled model, so like the PyTorch file, the TensorFlow checkpoint file, and you've got that, then you can work it out. But if you don't have this or something like that, you're basically cooked, it's not going to work. And the reason for that is this is essentially what is going to be, this architecture is what it is, how it knows what to do. And so when you compile it, what it looks like is, let's say for when I use PyTorch, when you train in PyTorch, you'll get a .pth file. So you'll do your epochs of training, and it'll say, number 1, 2, 3, 4, 5, whatever. I go to 20. So my 20th version, whatever one I elect, that's the epoch 20.pth. So it's a PyTorch weights file. And then from this, I need to turn that into an X model file. X model is like a generic model format that supports a lot of different things. So what you do is you turn it into this X model format, and to do that, you use, that's the Vitis, so I'm going to say it, Vitis AI that AMD has. That's that thing I was saying that's separate. You have to clone that GitHub, make sure you're on version 3, not on any other version it won't work. And then I got a custom script that I run, and it takes that .pth, which is like the PyTorch file, turns it into the X model. Then you run a quantization script on the X model, which turns it from the, well, you run it at the same time, sort of, but you end up with an X model that has got 8-bit weights. Then you can compile the X model file, and you run a command to blah, 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 compile X model file to DPU design 4000. And then it'll say, okay, cool, I'll compile it. Then it compiles it, and then you need to check. So you run an inspect program, you inspect your compiled X model, and then that gives you that stupid graph with the blue circle or the red circle, and tells you if it's all blue, then it's good. If there's any red, like bad. And yeah, so that's like probably the worst and hardest part of this. I could speak probably half an hour on just that. But yeah, and that's I mean, like, that's probably the hardest part of this whole process. But yeah, so any other questions or yeah, I'll just do it quickly.
Yeah. Like utilization wise, do you need an FPGA that chunky? Because that's fairly substantial resource.
Yeah,
Good
good question.
question on the
Yeah. So like, I definitely am gonna like try running it on like a Raspberry Pi, for example, run on different GPUs, just like whatever I've got access to see really, because this model runs like super easy, it's like a small model, and it can run on basically anything. So I think the FPGA like relatively kills this, like, but it doesn't kill it. It's like runs about 30 frames a second, but I think you get more out of it. Measuring the utilization is very hard because the FPGA doesn't intuitively have something to like measure the utilization. So what I'm going to basically do is I think I'll have to keep throwing in models of the compiler, and eventually the compiler will try to do it, and it'll say like, I can't do this. It's just like too big and won't fit. And so what I'm thinking is that my idea of getting a better FPGA was to be safe, that it will work, and these UltraScale Plus FPGAs actually support this compilation process. A lot of FPGAs doesn't even, this process will be possible. And then the other thing is basically that I can essentially just try bigger and bigger maps until eventually the map doesn't fit. And then that way I can say, oh, I covered actually. I can just say that it's, allows me more wiggle room.
Yeah,
That's all. Now moving on to yourself actually. Easy-PCB. So Project Origin for this one. UQCS Hackathon this year. I believe you guys won the hardware.
Yeah.
Or something like that.
Interdisciplinary.
Interdisciplinary, yeah. Very good. If you'd like to put, these on, you're welcome to.
Fancy.
And then that's the mic so everyone else can hear.
Yeah.
And your slides should be that should be on here. If they're busted, then I'm very sorry.
Awesome. Good evening, everyone. My name is Matt. This is Zach. We're going to present to you Easy-PCB, which we did 3 weeks ago at the UQCS Hackathon. Probably want to manage expectations a little bit. This is like a 24-hour project. It's not a thesis, but we think the idea is pretty cool. So we're just going to try and explain it to you as best as we can, and then if you have questions, feel free to shoot. So basically, for all those unaware, this is a printed circuit board, a PCB, and it's a bunch of fiberglass and copper, and its job is to make electrical connections. And so if you're just software, this is eventually what your code actually runs on-ish. Not exactly, but they're everywhere. They're in pretty much every piece of electronics. There's probably hundreds in this room. They're really, really important. But they're also really hard to design. So, I know you can't really see this, but basically there's a bunch of little copper traces, and they all have to connect different things on the board. And so when you're designing it, you have to connect those traces. But then as you lay traces, you block other traces. Because if you connect them across each other, they're connected, and you just connected your wires together. So it doesn't work. So what ends up being is a pretty tedious process, and there's a couple of tools that are being invented to try and speed this up. Because on large designs, this can be weeks of engineering time. Like it's a real pain. So auto routers exist, where you put all the components on the board, and it will try and connect them. They're not good. The one we made isn't good either. But we sort of took it a step further, and we tried to do the placing as well. And instead of just trying to solving it means different things depending on what you want to do. So if you're cool with having a massive board, then we can make a massive board, and it's going to be pretty easy to do. But if you need a really constrained board, well then we want to account for that as well. And so the idea is you have like 3, 4 different sliders, and you tune what's important to you in your design. So the ones we went with is board size, how components are spaced, the via count, as well as just general clearance around the rack. So it gets a little bit technical, but they're all things that you'd want to tune depending on your design. And we just want to make it super abstract, super easy. You tune the sliders, and that allows us to wrap the board based on your preferences. I'll probably hand over to Zach a bit, and he can tell you how we tried to do it.
Cool. All right. So This is a diagram of like a circuit schematic. So this is how you start your design process. So this is an example of a MOSFET driver for an LED. It's a pretty basic one. It was just something that's complex enough to prove that it works. Like a kind of a non-trivial example. So this is basically just showing all the components that you want to lay out on your PCB, and it shows how they're connected together. So in the software, you go through and you design this, and it basically then exports a list of all the components, properties of those components, like where the pads are, and a net list showing how all the pads will connect together. Then what happens is you convert it over to a PCB, and the software automatically places it in virtually a random position. It's then your job to go from this random thing, first place them in a less random position, and then connect all the nets. So this is the first step of what our program did. This is the somewhat optimized placement. So all these blue purple lines, those show where copper needs to go. So ideally you try to minimize the length of them, and you try to minimize how many times they cross over. Because every time it crosses over, it becomes harder for you to route. So what our program did is it went through basically all the combinations. It was a slow program. It went through a lot of combinations to try to work out how it can minimize trace length by trying to force, like using a force model to position them, and then adjust the orientation of all the components such that we can try to minimize how many trace crossovers there are. And it's done an okay job here. So it's a lot better than what it started out. Of course, this is a very simple example, and when you get a much more complicated PCB, like these become massive. One of the other things is PCBs aren't just one layer. They are almost always more than one layer. This one is 2 layers. The one that's being passed around is 2 layers as well. They can go up to like 24 layers. So for something like your motherboard in a computer, the CPU has an incredibly dense pin pitch. And so you need to use multiple layers. So not only are we about to try to solve a maze, we have to solve a maze in 3D. And as we're solving the maze, we're also making it more complicated for ourselves. And so this is the result of what happened. So it basically ran an A-star algorithm. It was a very modified one, where it would try to route a trace, it would pick a random net, try to route a trace, and if it runs into a block, it tries to make its way around, unless there is a shorter path going down onto the bottom layer and then popping back on the top. That bit also didn't work too well either. In terms of other things we have to optimize, we were talking about you want to optimize how well, you might have size constraints, and so your PCB needs to be a certain size. Often though, you want to try to minimize trace length, and you want to minimize the number of vias. So these grey circles, they're called vias, and they're what happens when you need to take a copper layer from the top down to the bottom. And the exact reasons why you want to minimize them becomes a bit complicated. But for a circuit like this, it's a MOSFET driver for an LED. And let's say you want to, PWM or control the brightness. You need to be switching it on and off pretty quickly. And when you do that, even if you're switching it at a low frequency, the edges of your voltage transitions are very sharp. And because of the Fourier series of square waves, you end up with really high frequency components of those voltage signals. And because of the black magic that is RF electronics, all the wires don't just become wires, they become inductors. And whenever you have a big pad like this, it doesn't just become a pad of copper, it becomes a capacitor. And so whenever you have these vias as well, it just does really bizarre things to your voltages when you're trying to either switch really quickly or switch at high frequencies. And so we're trying to minimize the number of vias. And so even manually designing a PCB is really difficult to do these designs properly. It's very hard to simulate these effects. And so you just try to minimize the results of this in the design process. Cool. And like this is the result of what comes out. So this is like a 3D render of the PCB. And yeah, it ran pretty fast actually. So if I were to design a PCB like this, it probably would take me about half an hour to route something like that. It took our program like 2 or 3 seconds. So there are significant time savings. Our approach isn't very scalable though. The Oliver factorial really slowed it down. The multiple Oliver factorial. That slows it down a bit on larger designs, but it's a cool proof of concept.
Yeah, so we're not really claiming that we implemented this particularly well, but what we probably will say is, from what we can tell, no one has tried to do the auto placing first. Though they'll just auto route will go, here's all the things, and I'll try and connect them, and if I can't, then I'll just die. And like the routing is very, very dependent on placement. If you organize things properly, it makes it way easier to route. So the idea, I think, is quite interesting. It actually probably has a bit of potential for someone who already has software like LTM to implement. Because auto placing first would genuinely speed things up a lot. And then you can actually have good auto routers, which would be really, really nice. But yeah, other than that, that's pretty much what we did in the weekend. Have we field any questions if anyone has any?
What are like your next steps from here? Will you try and like optimize that further factorial, or will you try to port it to more like PCB places like LTM?
It works with LTM in theory.
Yeah. So what we do is we just extract the file that contains the netlist. We know what needs to be connected to what. We run our program, and then it turns it into an importable file back into basically any PCB software. So compatibility is not really an issue. All-in factorial is for the rotation algorithm. Basically just check all of the permutations or rotations of all of the components and see which one has the least crossover. There's definitely more intelligent ways to do that. Yeah.
I don't think that's the biggest issue though, either. Sure, it eventually finds. Like, even if it's over factorial, whatever, that fine, whatever. Let it run forever. Our approach for the maze solving of like trying to actually route the traces just wasn't very good. The implementation was very poor. That was my fault. But I think just a better method of routing and better optimizing when it changes layers is definitely, like first it should work and then we can optimize the element.
Like, would you try to sell like, I know it's like a hackathon project, but do you have plans to like make it better and hopefully sell it, or like turn it into a business, or do you like intend on like keeping it like as it was?
I'd like to keep on working on it eventually.
It'd be cool if it worked. Yeah, to be honest with you, we haven't really discussed it since we made it. We haven't really looked at the slides or thought about it since we made it. But yeah, we do see a little bit of potential in it. So once sort of getting fried by uni, it could be cool to spend a bit more time on it and see where we can take it. Okay. To the question next.
My question got answered. I was going to say, how do you import it?
Yeah.
That was exactly what I was asking.
I don't remember the specific file types. I'll go.
Everything was remarkably standardized, considering that, there's like 20 different PCB design and schematic design softwares. It's a file type from the 80s or 90s or something, and nobody's been bothered to change it because it kind of just works. And so there's no interpreters for it, but we managed to reverse engineer these file types in the weekend.
That's pretty good.
It was remarkably straightforward. Just set file types. What was that? BS7 and SES or something like that. It was because you export it in a different file type as what you re-import it. So
Very good.
Well, one last question. How does sliders work at the start? Is it like some function you're trying to optimize based on those sliders position?
Yeah. So, like for instance, for the board size,
Yeah.
there was a few different approaches, but
if you saw how everything was connected with straight lines, what we do for the placement is essentially model the lines as a force, connecting a bunch of elements in space. So the slider just tunes how strong that force is.
Right.
So like it could be repulsive and really like try to shove everything out of the way or crush it in.
Yeah.
Stuff like the V account, that is handled in the maze solving algorithm. So there's a certain cost for going between layers. And that slider basically tunes what that cost is.
Yeah.
So that's really hard. It's like, try to do everything it can to not see layers. Otherwise it'll just do a little bit. Yeah, so stuff like that, just try to keep it really abstract. Cool. Well,
Very good.
Thank you for listening, guys.
Thank you. And so we've got Lewis presenting. I'll say what you're presenting.
You want to know what?
No, you're the man.
Alright, sweet. So I'm pretty much presenting how to do a technical thesis without doing any technical work. And so we'll use the actual title, AI-Based Innovation Support, Exploring User Motivations and Barriers. It comes from the HCI realm, if you guys remember that Deco 2500 course that they've done. So yeah, the major question is, how are AI chatbots helping people combat addiction? See, when I first saw this thesis, I thought no one actually did it, and that was actually an issue when we first started looking for data. But I'll just go a quick overview. The alcohol use disorder, just a condition. 400 million people suffer from it. 18 million in the US meet the criteria, and 10% receive formal treatment. I'll just rush through it. Why not? So there's some social factors of addiction, and some of them are like peer norms and cultural attitudes and social networks. And how to recover from alcohol use disorder is usually related to motivations in community, which is recovery and social identity shift, which is moving from drinking culture to certain communities that promote abstinence and accountability. Now, not everyone can do that. Not everyone has those communities, so what do? You beat up your friend, you go on the reddit.com, and you start talking to people there. Now, this may or may not have positive effects, but just if you don't know what Reddit is, there's 1.1 billion monthly users. You can use an alias, and it's free. To be for real, as an academic data platform, Reddit's actually quite amazing. It's accessible and free, there's no cost to recruit, and you get high quality responses because people aren't just phoning it in just to get $40, those research interviews. And then like I said, people are intrinsically motivated, which makes it actually quite good for data. But let me go to my knowledge gap. So it's a limited perception of understanding of how people might actually use AI besides cheating your coding assignment. So we've got how do people get around it, and then there's a few studies that use platforms like Reddit. Don't worry about it. You should be right. Scroll down. I did not do that. She'll be right, is what we're gonna say. You're just going down the slides now.
Oh no. I think I'll do it.
She'll be
We
right.
have an extra one.
A little bit more. Okay, perfect. We got ChatGPT's ability to respond to crisis and emotional need.
Okay, there we go.
Yeah. Lit. All right, we're back.
I shouldn't touch it.
Sweet. So we got our method, which is how we actually do all the work without having to do any of the work, which is our friend wsearch.com. I know it's a bit of a name. And so what you do is you fire in a bunch of communities that you want, Reddit communities, and then you put in the keyword, and it clicks them. So we see here we got stop drinking, AI non, and more stop drinking. And it's actually pretty sick. And so then I just go on that, I check the post, see if it's relevant, and then I scrape all the comments, and then I run a human analysis to make sure all the comments are relevant. Alright, here's the data. So we've got 4 sub-themes, I guess. We've got art, we've got the 12 steps, which is a US sort of recovery program. And we've got questions in math, and we've got support. So in art, we have some sub-themes around people using AI to make poetry, music, and stories, and we have personas. We get a certain type of personality you want the AI to respond with, which has made people seem more comfortable talking to the AI. Hunger the 12 Steps is actually one of our more interesting pieces of data because there are more negative comments than positive comments. That's what happens when I think you sort of break tradition, people get a bit upset. So that's one of the more interesting pieces of our data. Questions in math. related to people asking like, how do I translate my drinking volume from one alcohol to another? And I'll show a couple examples in a second, and support. Decided to shorten this down a bit, because it is. So we got examples of art. This is someone who used AI to create a sort of store like music, and then posted it up. It's pretty cool, pretty chill. Yeah, it's got some interesting words. Then we got like emotional support. This was one of the first posts I actually found when using like the search. I thought it was cool. Guy said he, stopped quitting alcohol, about 4.5 weeks ago and started running 3 times a week. And he was saying that he felt like the running was helping him sort of deal with his alcohol. And yeah, I responded with like, absolutely, running is one of the best tools for sobriety. And yeah, it's pretty cool. This one was like, the longer you stick with it, the more your brain will lean on running instead of alcohol to feel good. And that actually kind of spoke to me, even though I'm not an alcoholic, I do like to run. We're going to push into math. I thought this one was kind of cool. This guy saying like alcohol was a new drug, wouldn't be approved by the FDA, and ChatGPT pretty much, in long story short, says no. Saying the only benefit is the cultural and influence that already exists, which wouldn't exist if it did. And then we had like reactions, and so I forgot to add my reactions part, but I got a couple ones here. Oh my god. So we got like this one saying like from the ChatGPT get me help me get sober post saying that like it helped them bring a smile back to their face. Sort of saying like that's one of an example of a positive comment. And then we got another one down here saying that AI can't help someone because it's not an alcoholic. It's never been through it. So how can it know? Now, do they know? They can be an alcoholic. But pretty much. That's what it's saying. And that's one of the biggest in the community arguments that you can't use ChatGPT to help. And then there are people who use it for medical advice, and it is shocking and kind of scary that people do. And that's kind of it. So that's my thesis, but I thought I'd do a little chat about why do theses exist, and sort of helping someone decide what makes a good thesis for them. Because for me, I looked at trying to do more technical theses and realized that probably not a good idea. So yeah. There supervised open research programs to find something new or like research something new, and which has an underlying understanding that you're doing something that has not been done before. And so supervisors then are expecting someone who's familiar and hopefully proficient in the thing that they'll be undertaking. In my opinion, a thesis is not the time to be trying something new and overextending. It is a great opportunity to build upon existing sort of software that you are familiar with. So I got the tips who are looking to start a thesis soon. The biggest one is don't overextend your capabilities. There are times where failure is okay, and your thesis is not one of them, because if you fail it, you gotta do it again, and that's a whole year. Who really wants to do that? And there are safeguards in your thesis, such as drafts when you're writing it, but if you have no deliverables, then you have nothing to write about. So my biggest piece of advice is to write down what your strengths, familiarities, and proficiencies. When I first started, I wanted to do a project with blockchains and ML, and I had an interview, and I absolutely bombed it. I was kind of beg and double down, saying give me another week, I'll be able to prove it, and I spent a couple hours realizing that the extra stress of the deadline and uncertainty would not have been worth it. If thesis opportunity is a good resume project to get under your belt, if you are someone who already works in sort of a technical area like I do, I work in .NET programming. I found that it's more beneficial to spend 16 hours to 22 hours a week working your job rather than doing your thesis and trying to do something a bit more simple. And yeah, remember that everyone who passes a thesis gets to graduate. Now, everyone graduates to different opportunities, and maybe your thesis may open one up. But take on a challenge that you can do is my biggest piece of advice. And if you are someone like me who was worried about their skill set, here's what to look for. HCI is a very easy way to go. It's simple. And then, like I said, what meets your familiarities and proficiencies? And there's a couple questions to ask your thesis supervisor, because before you start, you have a bit of an interview with them. Ask what possible assistance they could provide in giving us proficiency. That's a big one. And if you feel like you may not be able to meet their expectations, well then keep that in mind. Another one is you have to submit a resume usually, so ask if there's any resume gaps in doing that certain project they may find. And one last thing is intrinsic motivation is extremely important because you're going to be doing this for a year straight, and then you do your semester of uni, you get the holiday break. A part of you is not going to want to keep doing uni, and so I really recommend finding something that actually that you're passionate about doing. And I've actually been quite passionate about understanding different AI use cases, so this was a great thesis for me. And I think that is me finished. So yeah, thanks so much. Any questions? Oh, there is. Sweet.
Yeah, I think it's really cool how you're able to talk on like a more like psychological topic in a more technical space. But do you think that like your supervisor or whoever's marking you will be more biased against it if you're not like including, I don't know, like crazy technical stuff as well?
My thesis supervisor is like the one who pushed me to go this route, so it's fine. Like that's why we learned like human-computer interaction is really about like the computer interaction between like users, and that's like why it's really easy. Is because you're not really trying to develop something. If you can open yourself up to doing more things, like originally I said I was going to like work on building an ML or like a wrapper that uses the data that I pulled in a way to give better support. And then I realized that I have no time to actually get that done, so I'm going to just get my thesis written and submitted.
Yeah.
And it's all about like your grades. Your thesis is graded by your supervisor, which has like a criteria in mind. So just try and like sort of meet that, I guess, is my best recommendation.
Yeah.
Cool, sweet. There you go.
Awesome. Thank you.
No problem.
Hey everyone, our team name is called Tygoon. We're a team of 5 people. I think some of us couldn't make it tonight, but us 4 here, we're going to talk about our project. The competition is like split into 5 parts, so I'll do a quick introduction, introduce the team a little bit, and then each of the 5 parts I think will have some more technical talks from the other guys. Sure, so firstly, just the game, like groundwork and the rules. So it took place this year in April, earlier in the year, from April 7 to 22. So the name of the game is money. Like you earn money, the more money you get, the better you are, the better place to get it. So the competition was broken into 5 different rounds. Every single round was broken into 2 smaller parts. One part was the algorithm, where you would submit a .py file to their online thing, and then they would return to tell you like how much money you made at the end of the round. The other part would be like a small manual challenge. This would be something like a bit of game theory, maybe a bit of financial math, and maybe just a bit of randomness thrown into our downfall. So what we have access to every single round is a historical order book. So an example of this is over here. So you have a price of something like rainforest resin, where you have something like, out of the entire market, there are 2 instances where people are willing to buy 2 rainforest resins for $10,000. There's also going to be people who are selling rainforest resin for $10.02, $10.00, and then if you have orders like this where I want to buy it 10,000 and I also want to sell 10,000, those are going to match, those are going to fulfill the market.
Are these the other teams that are in that order book? Or is it just like simulation?
It's just an example of order book.
Yeah, it's just an example.
The
But,
other teams are not in the order book. You're trading against pre-coded bots.
Okay.
That's the order book. So every round, your .py file, it's gonna like take in this order book, and you need to output like what buy orders you want, what sell orders you want, and you want to balance your risk and reward. So if you go like too risky or you overestimate, you're gonna lose that money. And obviously, you want to maximize your seashells. Okay.
Yeah.
Here's our team. A bit about me. I've got background in a bit of statistics, and I do computer science, so that's where I found my place in the team. I guess everyone else can do a bit of introduction.
Fair enough. Zac, was it the mic of the thing?
Both.
Okay.
It's recorded, that's why.
Gotcha. Hi, I'm Zac. I've been given a name on the board. Bit of finance, background in statistics as well, so I was sort of more of, I guess, research and trading, I guess, is the role I filled. Yeah.
Hi, I'm Zain. So I had a background mostly in like machine learning and dev work. So the role I mostly took is research and dev, but then towards the later rounds I stuck more to dev and then handed research to my friend Pradeep.
Yeah, my name is Pradeep. I'm a software engineer, but I do have somewhat like options pricing knowledge.
So this might be options driver, I guess. That's pretty much all I did here.
Okay. This is just a bit about performance. So you can see after every 5 rounds, we went up, we went down. Mentality changed a couple of times. We'll talk about that later. Overall, our algorithm performed quite well. So if you look at the global placements, our algorithm did pretty well. The manual challenge, as I said before, like it's game theory, so you're competing against other humans. There's a bit of financial maths, so we did pretty well. But there's also just a bit of randomness thrown in. So if you get on the wrong side of the bell curve, you're going to lose out on a lot of placements on the manual ranks. I guess, Masham's not here, but she did a lot of software engineering. She also cleaned up a lot of that code during the times. Okay, who wants to start with?
I think Zac started on both questions because you can't the market make market take.
Oh, yeah. So I guess initially we sort of very, very mean reverting. So the idea was initially, I guess, fit a process, which it was sort of somewhat okay.
Yeah.
But then we sort of found, because we looked at previous teams who sort of did quite a lot of similar stuff, and then we found a market making algorithm that was just enormously more performant, which is sort of a lot of the situation for a lot of the assets, which is sort of you try a base idea, which would be mean reversion or Bayes or something, and you think in theory it looks kind of great, and then of course something a lot more practical and is actually used in markets becomes largely more performant. I guess I'll move on to Zain to talk about the other assets. One of them being
Squid. Yeah. So Squid Ink was a bit of a pain in the ass, low-key. So in the first 3 rounds, we couldn't really get it right. It had massive swings. If you held a position, you'll just get absolutely destroyed because it would just swing in the completely opposite direction. So holding a position was the complete idiotic way to go about this. What we found is there was a mean reverting spread, and I can't remember what exactly we were mean reverting around, but it was some spread that I uncovered. I have to look at the code again. And then when we initially tried that, it was a bit better, but then there's a lot of false signals. So then if you just ran an EMA on top of that to clean out those false signals, it was actually very profitable. It stopped being really anal, and we could make a lot of money off it. So that's how we made a bit of money on Squid Ink. With kelp, there's a bit of correlation with rainforest and Squid Ink. I can't remember. I think we held more positions with kelp, and it just worked. So yeah, we made a lot of money in round 1, and then if we just go to the next slide, I think manual round or Pradeep and Zac or
mixture of the tools.
Yeah, actually, but come.
I really just assisted.
This one, to the side, it was basically just a transition matrix. This one we originally tried to do sort of efficiently, but then we realized very limited data, so you could sort of just brute force all the possible paths you could take, so 256, which resulted in basically everyone in the entirety of the tournament, I guess, getting the exact same and correct answer of that.
900. I think only 900 of us got the correct answer. We had a tied first place.
Right. Anyway, a lot of people, yeah, it was pretty much just brute force search through all the possible paths one could take. So I guess a mixture of the two.
As you can tell, when you don't have much sleep, you tend to just explain your strategies on Microsoft Paint. So in round 2, what happened is they introduced a basket, and each of these baskets had components. Immediately, neuron monkey activation, I just went, okay, this is easy ETF arbitrage, so what happens is if the sum of the components is greater than the price of the basket, I think, let me remember the directions. Would you short the components along the basket?
You just inverse whatever the difference is.
Yeah. Whatever, yeah, you just inverse the difference. So we did that first. I can't remember, pretty sleepy. But as I said, I drew it here in Microsoft Paint, so basically we'll wait for the theoretical price calculation of the components in the basket to cross over, and then that's basically our signal to basically hit the ground running and buy it. But, spoiler alert, if you go next slide, they barely fucking crossed over. As you can see, they never did, or barely did, so the signal just didn't execute. So what we did instead, we just market made until a signal presented itself, which also didn't make that much money because the would get absolutely destroyed by the bots when we were market making. So then, next slide, guess what happened? I met this beautiful man up there. If you haven't met this guy, his name's James Hurst. He's an incoming graduate trader at IMC. He did Prosperity last year, and I was just sitting up in Croc, so if you're doing Mech-Eng, you might get access to Croc sometime. And then he just walked past me. It's like, what are you doing? And then explained my algorithm to him. He's like, idiot. This is not ETF arbitrage. The reason is, if you can't redeem the sum of the components to an ETF, it is not, you can't do ETF arbitrage. That just doesn't work. If you can't create and redeem, is what he said. So if you can't create and redeem, you can't perform ETF arbitrage. So our theory was completely wrong. He instead said, what you want to do is regress the components in the baskets, and then it will uncover, I believe, some mean reverting spread once you clean the noise. If you trade on that spread, infinite money glitch. Unfortunately, we were so under the pump, we couldn't get it right. But then towards, I think, the final round, we got it somewhat right, so we still made a lot of money from the underlying and some of the baskets. Croissants was, the bots just like croissants. So we just had to EMA that one to see what happened. We did pairs trading for gem-based and croissants, so it'll be like a mixture signal between the two. We stopped trading gems because it was just bad. It was just a horrible strategy. And then we just did market making for the rest of it. And then, as you can see, we did pretty well, so we made a bit of money. Ignore the dips. The dips don't exist. But, the money went up, okay? It went that way. Next slide.
Oh, no, I really just helped me money.
Okay, this one, this is pretty much the only manual from here on. So it was, I can't remember how many containers, but it was basically containers had properties that would reward you depending on how many players would purchase them. So it was like multipliers, I think, inhabitants. The more inhabitants, the less the dilutive effect of other players. Importantly, we don't know the portions of how many people select each individual container. And so we sort of want to hedge, is the idea here. So of course, the noisy sort of manual trader would immediately just pick any container with low inhabitants and maximum multiplier. Turned out to be the correct move, but not for a logical reason. The reason being was everyone came up with a maxi-min approach, which is over here. So basically, we want to maximize what's the worst possible situation, which is, of course, maximum inhabitants, highest multiplier. It did get crowded out, but the reasoning, I think, was everyone had a heuristic framework that you'd put on top of your sort of game theory approach, which would then be, since everyone in the group chat, and it's a bit of a psyop, the group chat in Discord, so everyone would be posting all their different logics for which one would be the best. Some people were trying like surveys and things, of course, to try and estimate PK. I think someone told me they also sent a bunch of emails to get like a bit of sample data to try and estimate PK. But ultimately, a lot of people traded on what they call a break-even PK. So basically, how many people they could afford to sort of purchase or, I guess, choose certain containers or two certain containers before it started crowding out and, of course, taking away their score, which people did also try to get sample data for. But turned out, yeah, the people who picked the lowest break-even spreads made the most money because, of course, everyone was picking safe options using basically the same approach of just the game theory, maximize your worst situation, which you can solve pretty easily by just setting it up like that. Yeah. Round 3, I guess. Back to you again.
Options trading. I love options. Right, so round 3 was the introduction of, as you can see, options. So an underlying was introduced, that's volcanic rock, and you could trade 1, 2, 3, 4, 5 options at 5 different strike prices. A funny thing is IMC made time to expiry almost irrelevant because they expired after the competition was over. So great job. But what we found is in the later rounds, the strike, like the value of certain options decayed to 0 as they approach time to expiry, even though you can't exercise them before time to expiry, so it's really weird. But yes, it was basically just, can you options price? Next slide. This was, I think, our performance after round 2, so we've dropped a bit. Our algo wasn't performing like too well. We were like pretty disheartened. I kind of like went into a fit of rage and cancelled basically all the quant interviews I had for that week. So I had a coding interview with HRT, and I cancelled, I think, my 3rd round trader on Biftport. I was like, yeah, now I don't want to do this. So I was like, all right, full on lock in on this, and someone decided to push themselves a little too hard, and yeah, that was me. So what happened is, hold on, what happened is it was after I think the release of round 2. And I think I wasn't sleeping well, I wasn't eating well, I was like stressing myself a little too much. And then all of a sudden, my chest felt really tight and I couldn't breathe. Instead of calling an ambulance, I called an Uber. Because I was like, oh, I don't want to waste the ambulance time, I'm just going to call an Uber. Even though I thought I was like maybe having a heart attack. So I called an Uber like at 1 a.m. And then I got admitted to the ED. I was like, oh, surely this isn't anything major, right? And then I brought my laptop with me because I'm like, I still want to do work. I don't know, like, make the team like suffer or anything. And then I thought, oh, they're going to discharge me straight away. It's nothing serious. They're like, nah, mate, we got to keep you overnight. I think there's something suspicious with you. I'm like, great, okay. So what happened is I called my parents, and then I passed the phone to like the doctor, and then the doctor says, oh, you know, your son has an irregular heart rhythm. And then they call me, because they knew I was doing the competition, and they're like, you should probably stop doing this competition. I said no. I just kept doing it. So I kept going, and then while I was at hospital, actually, I was trying to read the options resources he sent me, because I knew nothing about options trading or anything. So he sent me a couple options textbook, and as they're trying to treat me, I'm just there like, options pricing must delta hedge. I was just like trying to read it as they're trying to treat me. I ended up getting discharged the following day, but they said, the doctor's like, bro, you gotta see a cardiologist after this. Like, you can't like keep doing what you're doing. Good news is I did see a cardiologist. It wasn't too bad. It was like, I had like an irregular rhythm for a week and then it went away. But yeah, they told me, don't do this shit again. And I said, nah, I'm gonna do it again. So that's what happened. Any of you watch One Piece? That's a bit of a One Piece reference there. But yeah, next slide. I made a visualizer while I was at hospital as well. So what happened is there was this guy named Jasper who made a backtester that everyone in the IMC Discord was using. It was starting to overfit by round 3. So the issue with the IMC backtester on the website is it only does cumulative P&L. So what I wanted to do is I made a visualizer that takes the P&L, because it outputs a CSV, and just outputs it per asset P&L, so we can know which asset is underperforming or overperforming or any issues we're having. And the other thing I did as well is rather than every round we're rerunning statistical tests, I just automated that. So I put all that in the visualizer, so any co-integration tests, order book analysis, and then it became more relevant in round 5 as well. Right, so I think we'll share this one around. So we defaulted to what everyone uses, so like Black-Scholes formula. It's like the bread and butter of options pricing. Pradeep here re-derived it by hand because we were not making money for a bit. So this guy whipped out LaTeX and was like, let me just re-derive what we're doing. Do you want to actually explain a little bit of like what you did?
So there's like a pretty standard options pricing like model. You pretty much have like a stochastic process that represents your asset price. You have interest rate, which is your bank, and then you kind of can transform to like what should be the fair price of your thing under a theorem called Kirznoff's theorem. But you could do it for a general kind of stochastic process. In this case, we stuck to Black-Scholes because they said use Black-Scholes, which was, I don't know, it just didn't work. And then even though we arrived it and it should have been correct, it still kind of sucked. So what I learned from that, I guess, for you guys is like, in one of these comps, keep it simple. Don't do like highly theoretical things. I don't think you need to. That's what I learned. But what do you guys say?
In terms of keeping it simple, I did a very, very like skibbity up. So what we did is we calculate the mean implied volatility of each of the different strike prices. That was, believe it or not, so we calculated that and then we grid searched it, so it basically defeated the purpose of calculating it. And then what we'll do is we fit a smile to the implied volatility, and then this loop over here basically if the current volatility deviated from the mean implied volatility, that's our buy or sell signal. So it was literally like, all right, here's a historical mean of the implied volatility. If it goes up, it's shorted. If it goes down, buy it. And it made a lot of money. This is not meant to work, but it did. So that's one thing to know with these comps is sometimes the most statistically correct algorithm might not work. You might have to do something real stupid and it just starts working all of a sudden. So if we go next slide. Yeah, these are round 3 results. So we actually climbed up quite a bit. We went back to 4th in Australia, basically 60th worldwide. Manuel still has a bit of work to do. We're back in the trenches, boy. But yeah, we basically were very happy. Our morale went straight back up. We weren't so like doom and gloom, so we're doing pretty well. Now time, I think, for round 3, Manuel? Or
round 3, if I go back, round 3 is functionally the same. This round 3, I think it was, instead of this, should go this one. Instead of this function, I think there was an extra fee. It was basically, instead of 2, you could pick 3 suitcases. The fee incrementally increased. But it's largely the same process. So it's just, and this time it actually worked. You used a maxi-min approach to get basically the sample space of what you want to sort of pick between, and then heuristics. So we sort of searched the, I don't know if that was super useful, but we looked at the forum page on the Discord they posted, which basically put everyone's sort of surveys and stuff and things like that. So we could try and get somewhere close to a moderately okay PK value. So what we actually think is going to be the distribution of the DGP. And I think we correctly predicted that we picked the least likely choices. So so there was like extremes of like 19 to 100, 19, 10, or like 1 in 10 or something. We picked exactly the middle, which would be the least picked. And the same theme of crowding out sort of existed. So we just picked the least likely. We picked the least likely, and I think we go to the. We'll see the book, but yeah, round 4.
I think we'll show them. Round 4 we kind of skipped over. We couldn't get it right. Basically, what happened is this was what I call exchange arbitrage. So a new exchange was introduced, and they're selling these things called magnificent macrons. You could approach this in a very macro perspective, in the sense of like, these are the 4 things that impact the price of the macrons. And the naive approach, if storage constraints didn't exist, is you would buy all the cheapest macrons from both exchanges, you'll hoard them, and then you'll sell them back to both exchanges at a better price. But you can't do that because there was a fee. Like for every tick that you stored macrons, that would cost you a seashell fee, so you couldn't just hoard them. So you would have to find, I guess, arbitrage between both exchanges and then just buy and sell between the 2. However, we couldn't get it to work because they sent another hint where they said sunlight hours and sugar prices, there's some model you can figure out and then you'd be able to better price or get a better fair value for the macrons. We didn't have time for that because what we were doing in round 4, if you go to the next slide, that slide. I'll talk about this in a second. But what happened is we're fixing all our old strategies. So we ignored this. So what happened is it would give you a false 50k profit, but what would happen is on the 100k tick, it would, like this is a short position basically that we're holding, it would fill the order book. Whatever orders are there, whatever position you're holding, it will fill the number of positions. So if the price is really bad, you're basically going to get bombed straight back to 0 P&L. So macrons we couldn't really figure out. Masham was trying to figure it out, but she got an eye infection, so I kid you not, she was coding blind when this was due, so that was pretty funny. If we go next slide. We still did pretty well, so Zac and Abhinav cooked on their manual rounds. Algo-wise, we went up, so 50th worldwide, algorithm 69, funny number. But we're still 4th in Australia, and yeah, we basically made a lot of profit. So now, round 5 is a fun one. So this is where you get to see the bots that trade against you. Me and Roger ran an analysis on that, so we were trying to find which bots were most profitable. I found Camelot to be really profitable for the volcanic rock vouchers, because as you can see, I hinted before, it decayed down to 0. There's basically no one's buying and selling these. because they're basically worthless. Backtester was overfitting, so we were making no money. And yeah, I was like, let me use Camilla to trade options. But unfortunately, Camilla must have not passed her probation at IMC because she just stopped trading in the backtest. So I think she got like, I don't know, fired 6 months in. The bot signals were really useless. We stopped using them afterwards. And then we go next slide. And then I found a disgusting revelation. So because basically we couldn't trade volcanic rock because we couldn't hedge it right, and our option, some of the vouchers went really worthless and we're making negative money basically, I basically turned on like goober mode. I was like, all right, let's try something really stupid. I'm just gonna run an EMA on volcanic rock. And I kid you not, we went from like just making 100K total across all assets in the backtest to 1 mil. That's in Jasper's backtest. So like we thought we were cooked. We thought we were gonna like basically bomb the competition, and then like an EMA basically saved us. So like back to the point that we're trying to iterate, like the simple approaches do really work. We literally around the EMA, suddenly we're trading the underlying really well, because an issue with the hedging we had is because of our big baller positions, we would drive the underlying as we're holding certain strike prices. So that was really, really bad. But this worked. Apparently EMA just solves all your problems. When in doubt, just really use an EMA. But yeah, that worked. And then if we go next slide. Actually, you have a lot to say about this.
This was interesting. So this one wasn't really, it was a portfolio task, so it was basically you had to allocate between 9 assets, I think it was, and percentage. So you had like 1 million standard capital you gotta assign percentage-wise. The important thing was you didn't get a returns vector, so no covariance vector, no returns vector, you just got like sentiment text, so just a bunch of news headlines. So the natural sort of first application was just use NLP, so just find some Python code or Python package online and then run the text through it, which fed us an interesting expected returns vector. So obviously, portfolio optimizer wasn't really the issue for this one, and this is where the element of randomness comes in. So you don't really know when to trust the tools and when not to trust them. So we sort of went on gut instinct, and the important thing was they were very, this like spurious sort of writing was the text, so it was really quite inaccurate in how it generated its expected return vectors, which when we fed it into the portfolio optimizer, we went the exact opposite position of what we should have, which would have jumped us up quite a few places. But yeah, the important thing here, I guess, is Minkowski, his expected returns vector is really, it's very important in terms of determining your weights vector. So yeah, make sure to read the fine print of what you're using, I guess. I'll give it back to you.
Alright, so these were our final results. So after a lot of blood, sweat, and tears and hospital visits, we came first in Queensland, 9th in Australia, and 89th overall. So we're pretty happy with it. Algorithmically, we did really well. Unfortunately, as Zac was saying, we got really bummed in the manual round. So one asset we made a lot of money, and then the one that we went the opposite direction in completely negated all the profits we made in manual. So we made a nice $1. So I mean, I can use that at Hungry Jacks. Like it's not really that big of a deal. But yeah, we did pretty well. It was a lot of fun. So then go next. These are our takeaways. Like if you want to take away something from this presentation, this is what I'll tell you. Call an ambulance instead of an Uber next time. So don't do what I did. At least don't get into the position I did. Something I picked up from Zac, which is a really great hobby of his, is read books and research papers. Like reading books is really, really good. Reading research papers as an infinitesimal amount of information. We kind of tried to avoid websites like Investopedia and that sort of stuff. We just went straight to like research papers, see how other people have done it. A thing that allowed me to contribute as much as possible to this competition is I finished all my assessments a month in advance before the competition, so I walked into it, I could skip all my lectures and shoots and not worry about due dates or quizzes. This one is, do not neglect your health during the competition, as I've evidently said quite a little bit. This one is more for like newer members. Don't blindly GPT your strategies. Read the book first, read the research paper first, understand it, and then once you kind of have a heuristic for the algorithm, you can then use AI to help you. And if you do use AI, maybe don't film a reel about Also, have a good mix of skills in your team as well. So as you see, like in our team, we're very diverse. Like Abhinav is really experienced with compilers and like very low-level stuff. Roger was also with Oracle with them, so he's very experienced with certain algorithms. His grid searcher basically saved like half our like strategies. Zac was really smart statistically, came from BAFE as well, so a lot of the finance knowledge did come from him. And me and Masham kind of had like more software engineering experience, so she was at Amazon, she was more familiar with clean code, clean practices, and I'm just the ML gooner basically. So we had the wide like range of skills in our team. And then the thing is with these comps, you might feel a little bit intimidated because it's a worldwide comp, there's like PhDs competing against you, there's everyone competing against you. If you go in to learn, you'll be fine. Right? If you go in just to learn some things, you can always try every year. Most people are doing 4-year degrees, 3-year degrees, 5-year degrees. You've got 3 years to do this. Like, you got heaps of time to learn. With Prosperity, this was single-handedly the most talked about project in all my interviews. Optiva was frothing over it. Every firm that I interviewed with loved it. I think Prosperity might have been one of the only reasons when I did my SIG final, they put me onto the tech stream because they're like, you know how to code strategies. We'll love to put you maybe tech stream possibly. So if you do comps like Prosperity, these firms love it. It's a gateway into these firms. Unfortunately, somehow not IMC, because we thought IMC would like it, but like they didn't really do anything about it. But in the end, just have fun. I didn't know Zac before this, I didn't know Abhinav before this, I didn't know Roger before this. We became really good friends out of this. So go into it, you guys, like coming out of Prosperity is like suffer together. You come out really good friends. So I think that's really, do you guys have anything to share? Some words of wisdom?
Summed it up pretty well.
We kind of yapped, but we haven't.
I have a question.
Yeah.
Just for those who haven't competed, like, let's just say on average per team member, how many hours do you think you put in like per day or for that whole week? Because I know it doesn't look like much, but the hours that go into that is like pretty ridiculous.
I think we all put on a lot of hours. I think, well, for me, because I have a lot of free time, for at least 40 a week.
Yeah.
Yeah. How many hours like you should put in?
For me, primarily, I kind of like hopped in at the later end of this thing, I've done some stuff first week of it. Pretty much I was only like kind of into that first week. So yeah, second week, pretty much, was also during the holidays, I believe.
No.
Mid-Zealand. Yeah, mid-sem, like whatever we had there. And I was like, oh yeah, so pretty much spent like a day or two with Zac, whenever we had to submit close to it. So yeah, pretty much full time. Latter end of it, I guess.
I guess I'm a bit different. I think the main carrier of our team is definitely like Zain, Zac, Abhinav, Masham. I think you guys did the bulk of the work, just not me. I think
You grid searcher though, bro.
Let's say. I'm not a prolific coder. I'm not a prolific mathematician, but I did a bit of research on the side notes and stuff, and I just had fun in the game.
And how many hours do you think?
Yeah, probably 40 a week. Yeah, probably a fair estimate.
Yeah.
Did you guys know a lot of these concepts before you came into it, like arbitrage and whatnot? Did you know?
Yeah, well, Pradeep and I worked on the underlying sort of processes and math behind. That's probably better. Pradeep and I worked on sort of the underlying statistics and math behind a lot of the trading sort of, not sort of the trading ideas, but more so like how to trade on BGPs and stuff. Data generating processes.
Thank you,
Which is more important than sort of knowing them outright, because a lot of them you sort of build up from either your trading band, well, I wouldn't say Bollinger Bands, but you're basically trading bands on a mean reverting spread or like some sort of BGP like that, or you're sort of betting on some sort of long-term drift. But yeah, ultimately it's just a bunch of statistics wrapped in a bunch of fancy names. But yeah, Pradeep and I did do a bit of the work like beforehand for the finance, and of course the software engineering work. They definitely have done really quite a lot of similar portfolio sort of stuff ahead of time.
And what year of your degree was like? Did you cover that stuff in your degree, or was that stuff that you had to cover outside of your degree?
Sort of electives, yeah. So yeah, a lot of like I think fourth year stats stuff is sort of where this a lot of this stuff comes from.
Yeah, gotcha.
But the underlying like value stuff is there's a lot of finance basically. So it's sort of like try to find a way to estimate value, and then the tools are just the stats.
Yeah, well, very good. Good stuff. Well, thank you.
I think we walked into it not knowing much finance. He basically gave us all the resources, and then we walked out of it very confident in all these techniques.
Yeah, well, yeah.
So like if you genuinely want to learn these techniques, like Prosperity is very good for it. Like that pressure, that like expectation to perform, it teaches you a lot.
Yeah, gotcha. Yep.
Oh, so the winning global teams came from like IIT. I think one of them was German, and IST, which are they're basically like the Harvard of India. They're very, very hard to get into. And basically, funny story about them, they got caught cheating in the first 2 rounds. So they were hard coding their strategies to the bots and basically milking the crap out of the bots. And then the German team was like, we're going to be nice about this, and reported it to IMC. And they got shafted in round 3. So they were allowed to resubmit strategies, but their score was deleted. And they came from that university because like IIT, IST are very, they're like MIT's instance, they're very technology like dense, if you know what I mean. Like the people that come out of there are super cracked. You know, like some of the smartest people out there. Like some of the people that competed in this are quants at Goldman Sachs, or are quants and HFTs, like interning there. So they weren't eligible for prizes. So for context, if you are going to intern in HFT, like you have an offer to intern, or you have interned, you're not eligible for prizes in Prosperity. So those guys didn't win prizes. They just come in to kind of take the piss and like bully everyone. So yeah, IIT is a very, very smart university. Like they're like the MIT basically.
Where did you look for your research papers as well?
A lot of them are from like sort of lecture slides. So like course catalog sort of gives you a lot of them. And then just sort of surfing around. So when you just sort of look on like SSRN, like archive and stuff, you sort of find the top papers. If you look up a certain strategy or like a certain kind of like price dynamics, you sort of run into the main papers people use. GitHub as well is a big sort of source of it. So like finding source code implementations, they usually have either a thesis or like at least a project they've got. But yeah, it's mostly just like the paradigmatic stuff that people use is the main way you find it.
Thanks. I think that we will. Do you have room
Yeah,
for one more?
one more.
Alright, last one.
Yeah, did you say you had some good textbooks that you used to learn all this stuff? Books or something?
Well,
just research pages.
There's a couple. Like he found a heap of PDFs. I think there's what's the statistical arbitrage book he sent me?
Yeah, there's a couple. I can't remember the name, but it's one's like statistical arbitrage is the big one to sort of get into how price discrepancies work. Another one's pairs trading. I think it's by the same guy. It's like a yellow cover.
There's an options one I found. There's one I found in a book fair. It's called Volatility, Hedging, and Correlation, and I think the White Fox. That's what it's called. Yeah, that one. I got it for like $10 on like one of the book fairs. That one's really good. Really, really good. Teaches you a lot about options pricing. The one you sent me, there's that YouTuber that you sent me. There's
a couple. It's like Hull's obviously your main one. It's like options, futures, and derivatives.
What was that?
Like John Hull, I think is his name. So it's options. It's the main book, options, futures, and derivatives. There's also like dynamic hedging. I think is the main one. It's pretty old. Yeah, and like option pricing and volatility is another pretty good one. And then just like your main statistics books. So like using PCA or using like any sort of the tools is just being any of your like stock standard statistics books. Yeah.
Okay, thanks.
Thank you. Awesome. Thanks for answering all the questions. Last but not least, we've got Carl Flottmann with another FPGA kind of based one here, which I thought was really interesting, and we share our supervisor Matthew D'Souza.
Okay. The reason I'm here is because I put in a PSA to the Thesis group chat saying, can anyone help me with a problem I'm having? And Max said, come present. So I'm here now. So this will take a little bit of a different turn. Most of you guys are onto the fintech stuff. I have no idea about that stuff. all of what you guys were just talking about is beyond me. Good luck with the dough. I'm into cyber security. That's what I do. So I'm a 5th year electrical engineering and computer science dual student doing a thesis with D'Souza, and it's on an FPGA-based network intrusion detection system. This is just the seminar slides I have. I haven't seen these since like April when I presented them. So a little bit of progress, of course, has been made since this, but I'll try to, speak through stuff that is just like there for the criterion and try touching stuff that I actually progressed on since then. So what am I doing? So I'm focusing on a network intrusion detection system for edge IoT security. So when it comes to cloud computing, we decided that things were getting really slow because we originally had this cloud layer connecting with our edge IoT devices. From your phone, you're connecting straight to the cloud. Everything was really slow because if I wanted to run an intrusion detection system, so it's just me trying to detect that there is an attacker on your network, it would have to go through the cloud layer and back. And we want this to sort of act like a forwarding process because we don't want these packets to actually reach you if this has an attack. What are some of these attacks? I don't actually have these in the slides, but some of these attacks might be DDoS is the big one. You can actually see a live map of DDoS attacks currently if you hop on something like Shodan. There is an absolute massive amount of DDoS attacks, like terabits per second, currently happening at the moment. You can see them live, and that's the kind of things that we're trying to detect here. What is my next slide? Some motivation. There's a ton of vulnerabilities in this stuff. So one of the big issues that mine's focusing on resolving is something like the 2016 Mirai botnet. So what happened with that was there was a bunch of IoT devices that were vulnerable to something. Some Russian hacker guy just said, great, I'm going to just blast this across the network to get a hold of all your devices. He got a hold of billions of devices, I think. Do I have a number here? No, I don't. Yeah, it was in the order of billions, and he launched the largest DDoS attack in history. He took down a few governments, and he took down a few major firms. That's obviously problematic. So that's why this kind of thing that we're doing is required. So a bit of motivation on why am I doing this on an FPGA other than the fact that I'm told I have to. You were heard from Max earlier, so all of you are reasonably familiar now with what an FPGA is. Quick recap, it's programmable logic. You are programming the FPGA to basically act as a specified circuit, and it'll run for the function of its duration until you reprogram it, it'll just switch it off or it blows up. And so that's what makes it fast. You've got hardware accelerated logic. The reason why I want a network intrusion detection system on this is because I want to handle really fast network speeds. So if you've got one of these inside a data center, you're doing things in the order of gigabits per second. Some data centers are now in the order of terabits per second. And so you don't want your network intrusion system to be the bottleneck in it. And so that's why you'd like to write it on something like an FPGA. But as I mentioned earlier, we're doing this on the edge. So we actually need these to be really small. So that's why we've got an FPGA, because that's a small embedded system. This was marking criterion. So was that. I'm doing mine with machine learning. So I found a few papers that actually had some sample resources on these, and I was able to build upon them. I'll touch more on these later. Basically, the rule-based algorithms, you have to do a lot of design in Vivado. Vivado is really big, scary, and it's taking up way too much space on my computer, and I kind of don't want to deal with it. So the machine learning is actually a much better option for me. I can simulate everything before I actually run it on the hardware. We can kind of ignore this, but basically I'm trying to make mine have a really high level of detection performance. I'm trying to make it really small, and I'm trying to make it really fast. To give you an idea of kind of size, we only have spaces in the order of kilobytes of FPGAs. And many of you may have dealt with our models before. They're generally in the order of megabytes to gigabytes. So getting something down to something small enough on an FPGA is actually quite challenging. Max gave you the example earlier of what Vitis AI and all the really complicated compilation stuff does. Mine's a little different, but they all focus on making really small, fast-running models. So what am I doing? Mine is using a weightless neural network. So these are specialized types of neural network. A usual neural network will have something that runs with multiplications. You generally have nodes that are performing multiplication operations. Now these are really expensive pieces of logic in an FPGA. They're generally actually specialized logic chips, I suppose, but the sectioned out part of an FPGA, you can only use a certain amount of them. I think, like my board has something like 48. There's not a lot of multiplication operations that you can perform. So they're really problematic. So we started looking at these weightless neural networks. So instead of multiplication operations, you do these table lookups. So you have a RAM node, like what I'm showing here. It's just something you have n inputs, and then you have 2 to the n entries inside, and that gives you a result. And what you do is you combine a bunch of those and sum them together using a pop count method, and then that is one of your discriminators. You combine a bunch of these, you do some really funky routing to map everything to the individual RAM nodes in these discriminators, and then you're going to get a result. The problem with these, many of you other guys may have already noticed, is you've got 2 to the n entries in your RAM block. That makes things increase in size very, very quickly, exponentially. That's all the things I just said. But it was really accurate, was the cool thing. This one was only 192 bytes in total size. Now that's actually incredibly small. It's the smallest model that I could find, and I reviewed 100 papers. So that is quite a small FPGA model. The biggest issue with this one, and it was fast, order of gigabits per second. But the biggest issue with this one were the input features. So the input dataset this was trained on is called UNSW-ND15. That's actually trained by our mates down at UNSW. They offer that on a SharePoint for some reason. That actually gets flagged as malware when you access it. Anyway, that has what are called connections over time features. So things like the total duration of a connection may be in a feature. And that's something that builds up over time as your network functions. Now, that's not going to be particularly useful if I do want something to run at gigabits per second in real time, because I have to wait until the total connection of my network is done before I actually tell you whether you've been attacked. And by then, I've already installed the crypto miner on your computer, so anyway. Yeah. So what did I do? I found another open source repo. This one used real-time feature extraction to do this. So they actually use the raw bytes in your network payload to perform the detections as opposed to all the funky features I've shown you earlier. But the problem with these is actually ordering them in a good way. So the previous paper that I don't have up here because it was kind of useless, but they just started shoving bytes into the weightless neural network, and they got something in the order of 30 to 40% detection rate. The SOC engineers who would be reviewing that would kill themselves within a day if they had to deal with that level of false positive rate. So that's not ideal. So what they did is they started sorting things based on the flow identifier. So that's made up of your source, destination, IP, and port, and the protocol. And they're just typical standard headers that you require in every TCP or UDP packets or other protocols as well. So you use these, you sort them into buckets, and a bucket is going to contain some amount of packets that is fixed, and it's going to take a fixed amount of bytes as well, and then you're going to get your funky 2D input that you can now use as input to your AI model. 2D inputs is things where our AI people will know we are happy with these, and we can use these as input to our AI model. These guys, though, they use something similar to what Max is doing, a convolutional neural network architecture, and they quantized it down using something similar to Biden's AI.
I think that's the TensorFlow one.
Is this the TensorFlow?
I think Fin is the TensorFlow, or maybe the older version of the one I'm using.
Okay.
So it's same workflow.
Yeah, kind of same workflow. You quantize it, go through a really bunch of annoying compilation stages, and that pops your model down onto your FPGA board. Really high level of test accuracy, but it basically took up the whole FPGA. We want it to be much smaller because the FPGA is going to be our edge IoT node, so it also needs to do a bunch of other things like routing, actually storing data that you're getting from all your other sensors. So it takes up almost all of your resources that's not particularly useful. So my proposed solution is I'm going to smush them together because I've got two open source resource code bases that I can use, and I've got two different ideas that I can smush together to achieve the three highlighted in blue design criteria I was showing earlier. So what does this look like? I don't have a Vivado example to show you because I've got to install it on an app. But basically it looks like this. I'm going to take incoming traffic, I'm going to shove it through the PS. For those unfamiliar with the FPGA stuff again, the PS is the processing system. So if any of you have done any of the embedded system classes dealing like 3010, 2010, what you guys are programming on is PS, it's a processing system. You program it like an embedded system in C, it runs on the CPU. Now the PL, as well as discussing earlier, that's not programmable logic. We write that in a hardware scripted language. It looks the HDL system Verilog, and it's a very different way that I can really show it later. But the thing that they share is the DRAM, and the DRAM is what we're going to use to shove our packets into the DRAM. I'll do a bunch of fancy things, active DNA is can't get to work right now, but we'll use that to extract it, shove it through our bucket sorter into my model, and then pipe it back out. Tool selection, honestly, didn't have a lot of choice. I have to use Vivado because that's the only thing my board is compatible with. I didn't want to buy an FPGA. I eventually got given one, and it only works on Vivado. So that's why I'm using Vivado. But it also has all the cores that I need. So the DMA is something I do not want to write myself. And so I can just pop that in. Vivado, for a lot of FPGA things, you can actually just pop things in like blocks / connect the dots. There's also a bunch of connection configuration it can run for you. So a lot of that is automated and then you don't have to worry about it. Also, I thought that's a different issue. And then the other thing I'm using processing system is Zephyr. So Max discussed earlier, he was using Pedalix. Pedalix is basically an embedded system design Linux distribution. Zephyr is like a slightly more what we call bare metal version. So Xilinx, who procure the boards, they do actually provide their own API, but it's particularly complicated and you have to custom write all the stuff that Max is doing. Zephyr is kind of like an intermediary one. The only problem is it is open source, so no one documents anything. And that's why I'm liaising with a random guy in Germany right now about my problem. But the deal is Zephyr is going to make it slightly faster because it's slightly more bare metal. So the actual AI model training. So we just try and test optimize all that business in PyTorch. I had to email the guys in Frankfurt saying, please give me more space. You only give me 5 gigs, I need 50 gigs, please, please, please. They eventually gave it to me. And once I've got the model in PyTorch, though, the trick is getting on the FPGA, as Max has so happily discovered. What I'm doing, and what was kind of already done in the code base I've been using, is we use these things called macro templates. So once I train it, it's actually going to give you a bunch of parameters. Macro templates basically lets you write any kind of file, template it out. So in my case, system Verilog, which is a code file. But you write some of the parts in Python so that when you render it, it runs that Python code and then it spits your file back out. And so that's what these do is they render the configuration based on what my AI model actually trains, and it spits it out to VCS synopsis, and that like does all the verification, make sure it actually works. I don't want to pay for it, so I instead ported that over to Verilog, which is just a free open source and slightly less annoying version of that. And the rest of that is just like semantic stuff. Yeah. Since then, I don't know if last word because I haven't looked at these. Since then, we have got it working. I've got it working in PyTorch, and I've got it working in System Verilog as well. I'm getting a 99% detection rate, it's fantastic. Theoretically, 400,000 samples per second, which is pretty fast, and then it's only about 6 kilobytes. So now I've got to keep liaising with this random guy in Germany to get my thesis working. That's all I have.
Just a quick question. My question was, would you just be able to like elaborate a little bit on what particularly you're liaising with like what you're trying to solve there, I guess, with that guy, because I thought that was kind of interesting or funny.
Yeah. So what I was showing you before, is this? No, that's something else.
It'd be different slides.
I can't bother to do that.
Yeah, it's all good.
What I was showing you before, I was discussing the DRAM and the AXI DMA. So DMA, for those of you who haven't seen 3010 yet, get keen. Direct memory access. So instead of accessing all the memory stuff, which you usually do through the CPU, go through a bunch of really annoying little things, and then eventually go out to memory. DMA is basically go straight to the memory, pull it out, and pull it into my system. So much faster. You have this actual DMA controller that handles it for you, but that's the only intermediary. To liaise with AXI DMA in Zephyr, you need like a driver and to pop something in what's called the device tree. So it means you just state, I have AXI DMA and it's located here. And then the guy in Germany wrote a bunch of really complicated, long 2,000 line C files to actually interact with that thing. And what I'm talking to him about now is every time I use it, it tells me that it can't access the memory location and that it's not there. And that's the current issue at the moment. Vivado is very fancy. You can do a lot of different things with it. So you can, if any of you have done any embedded systems, you may have used logic analyzers before. In Vivado, you can actually use an integrated one, so it turns your computer into a logic analyzer, and you can actually see all that business if you plug it in, like Max had with USB, and see all the signals. So I'm changing that.
Question for you and Max, like these monoliths getting compressed by like orders of magnitude, what kind of performance hit do you see from them?
So for mine, it's something that I've actually found in my thesis. So Max was discussing earlier with the pruning. So generally, if you want to quantize a model, like Max mentioned, you're kind of losing accuracy already when you try to quantize it, because you're making this smaller, it's going only fixed point integers, you don't just have the infinite integer size for yourself to deal with, right? And the pruning, what that does is supposed to account for the loss in accuracy that happens when you do the quantization. So usually, like what mine does is it will find all the filters, all the discriminators that just aren't firing, so like they're not doing anything, or they're just really lazy, or barely firing, or they're always producing like the same result, they're always producing maybe zeros or ones, and it'll actually get rid of them or rewire and remap the inputs to them, and then it'll retrain the model with that new rewiring and mapping to see if that increases accuracy. That's what mine does. The interesting thing with mine, so most models work that way, the interesting thing with mine is it doesn't require that. All the input mapping and rewiring already fires enough, and that's because I'm using the raw bytes and bits as I was describing with the input features earlier. Traditionally that's how you do it, is you rewire all the inputs so you can squish it down further. And you can generally configure like the percentage of pruning and like squishing that you want to do. There is definitely a loss of accuracy, and it's like a trade-off that you have to kind of like